Let's take some time here to talk about exponential models, and what we're talking about are some common differential equations that we might work with. So an exponential model is any differential equation or any function where the rate of change is proportional to the function itself. And this is most commonly seen in populations that reproduce. So if having more of something means it's going to change faster, that would be a good place for an exponential model. And it's called an exponential model because the solutions are exponential functions. So pretty self-explanatory here. We're going to look at two examples of this. Usually we see these in populations. Because the more animals or the more money or stuff that you have, the more you see it grow. So find the particular solution given that g prime of x is equal to 7 times g of x and g of 0 is equal to 5. So if we want to solve this, we're going to need to rearrange it. So I'm going to write this instead as dg over dx is equal to 7 times g. And that's just, whereas we've seen before, like with y prime or f of whatever, I'm just rewriting it in variables that I can work with more easily for separation of variables. So rearranging this, we get 1 over g dg is equal to 7 dx. Integrate both sides is equal to integral 7 dx. So that means we get natural log of g is equal to 7x plus c. So g of x is equal to e to the 7x plus c. G of x is equal to c e to the 7x. And if I have g of 0, 5, that means g of 0 is equal to 5 is equal to c e to the 0. So that means that c is equal to 5. So g of x is equal to 5 e to the 7x. So again, it's just separation of variables, but it starts from the fact that the rate of change is proportional, directly proportional to the function itself. The next example here will kind of help reinforce this point. So the value of a certain investment increases at a rate that is roughly proportional to at any time to the balance at that time. So what they're saying is this is an exponential function or an exponential model. If the investment started at $1,600 and is at $1,920 after 1 year or 365 days, what is the balance of the investment after 90 days? Well, we need to start off with a couple of things. First, let's write a differential equation. So we'll say d of the amount of money divided by t. A lot of times we'll use p for the population or for the principal if it's in finance. So the rate of change dp over dt is some unknown constant times p. We don't know what this constant is, it's just something that we'll be able to solve for later. So dp, 1 over p dp is equal to k dt. Integrate both of these sides. I'll leave it if you need to double check this on your own, go for it. But we get ln of p is equal to kt times plus c. So p will equal to e to the kt plus c. P is equal to ce to the kt. If you've ever seen the equation for continuously compounding interest as the amount is equal to PE to the RT. That's just this solving for this really simple equation. Okay, now we have two bits of information, 1920 after 365 days and 1600 at t equals 0 days. So we've got two equations, we have two unknowns, we can solve this. So $1,600 is equal to CE to the K times 0, and $1,920 is equal to CE to the K times 365. Well, in this first expression, we see that C is equal to 1,600. So that means we can rewrite this as 1920 equals 1,600 e to the k times 365. So if we want to solve this, we need to take the natural log of both, well, divide 1920 by 1,600. Take the natural log of both sides, and that will give you k times 365. I do not have a calculator that can calculate that really quickly, so we'll just say that k is equal to something. We don't know, well, I mean, you can go through here and solve it. It'll be ln 1920 over 1600 divided by 365. Then it's just a matter of going back and saying P is equal to 1600 e to the k, and then instead of putting in an unknown t, we'll put in 90, and that will give us P of 90 days. So hopefully this is pretty clear, pretty straightforward. Exponential functions are nice and easy to solve because they're always just a constant times the population or times the amount of money, something like that. So they'll always work out to this pretty nice function of CE to the KT, or if you used other variables, PE to the RT, something like that. And this will lead us nicely into the last type of model that you'll see in the next video, which is logistic models.